And yeah, I'm very happy to be here and see many of my friends and colleagues. So, this work actually all started in IPAM, as it typically happens in these talks. So this was a collaboration that started in this AHJ 2020 program. So Hamilton-Jacobi was a long program on high-dimensional Hamilton-Jacobi equations. Unfortunately, COVID came along and many of the events went online, but that didn't stop us. So the collaborators on this paper that I got to know from this program are Yunan, she's now at Cornell. Rob, he's now a program officer at the Army Research Office. Eliza is here, sitting there. And Mireta, I think she's in Virginia Tech. So Adam Oberman is not on the paper, but he played a pivotal role because he gathered all of us and introduced all of us and then said, I'm too busy. So you can just talk to each other. And so we talked to each other, and this paper came along, but he played a pivotal role in this. So IPAM played a pivotal role in this. And actually, yesterday there was this very nice panel discussion, and some of the panelists were saying that, I think scientists and mathematicians sometimes think that it's self-evident that research we do is important and the funding for such research is important, and institutions like IPAM are important. And I think in this vein I want to acknowledge, with one slide I want to acknowledge the funding that we got, that the institution gets from the NSF and other sources. And there were a couple of programs that were pretty pivotal for me personally, but also I believe for others. So there are these mean field games, two mean field games workshops and summer schools that were hosted by IPAM, and Stan might correct me, but they're also funded by this big Emory grant where Stan and Wilfried were PIs on, and later that grant actually funded me while I was at UCLA. And actually, I think it was either on this workshop or this one where I first met Stan, and he got me hooked up on computational methods and of course the L1 stuff. So it was pretty, pivotal for me. A semester before that, there was this machine learning for physics and physics of learning, where I met Lars, and I think maybe Lars and Stan knew each other before, but that's when we got to work on these machine learning methods for mean field games. And we can see a couple of talks here that there's some ramifications, and it was a big influence for me. So I want to thank the Institute and all the funding that is supporting these activities and our work. Okay, anyway, so let's move on. So system identification. So what is the problem that we're studying here? So let's say we have some dynamical system, and here I assume that it's an autonomous dynamical system. It's given by x dot equals to v of x. We have some observations of this, and what I want to find is the dynamics rule, or the policy, or the velocity field. You can use whatever name you're more comfortable with. So typically there are two settings when we're trying to solve this problem in terms of approximating this velocity field. You might have like a model that comes from physics or economics, where these parameters theta, they represent some physical parameters that need to be estimated. Okay, so these are, they have physical meaning or meaning from economics or elsewhere. Or you might just have a mathematical approximation of this velocity field by a universal approximation theorem. So you could assume that V is polynomial, or you could choose other basis functions, you could choose neural networks, and etc. And the parameters that you're trying to learn, that you're basically trying to recover this velocity field, are expansion coefficients for basis expansions, or neural network weights, or something like that. Okay, so in either case, you want to find the optimal, or the theta star, so you want to find a set of parameters that match the observations of this dynamical system best. So that's the goal, that's the overall goal. So first, let's start with the data. And typically, these types of problems are solved using Lagrangian approach. And what I mean by this is that we have observations of the dynamical system at certain times, t0, t1, tn. So here I just represent one path, but you can have actually multiple paths. And what you're trying to do, you're essentially trying to find a set of parameters so that if you run the dynamical systems, that path will be close to this path. So you're basically matching time series. Now, for problems that have, for example, for chaotic dynamical systems, one issue is that there is an instability with respect to initial conditions. So here on the right top, you see two paths. So of the Lorentz 63 system, which is this well-known chaotic dynamical system. So the initial conditions are very close. And as you see below, like initially, just because of the continuity properties, the paths are pretty close. But then as you move on, they start to diverge, and then the correlation completely goes away. So if you're trying to learn using trajectories, you have to be aware of these instability issues. So a workaround around that is to look at the trajectories from multiple initial points, and I'll come back to that point. Another problem is that if you have slow sampling, so if these time intervals, if the gaps between the time intervals are large, then the finite difference approximation of the derivative, and you have to approximate the derivative if you want to match trajectories, might not be accurate. So it might not be possible to even approximate the time derivative. Okay? So these are the challenges. So what can we do about it? So what can we do in situations where that Lagrangian approach is actually, it's problematic or sometimes even impossible? Well, we go to Eulerian approach, and what happens is that sometimes some systems, they have well-defined statistical properties when the time is very large. Okay, so although they might be sensitive to initial conditions, but their statistical properties for the long time are actually well behaved. So how do we say this formally mathematically? So let's say B is some subset of your phase space or state space, and you have this dynamical system X, so X is the trajectory. You look at this measure, which is called the occupation measure. So it depends on initial condition X and then the capital time T. And so you just basically, for a set B, you just count the fraction of the time your dynamical system spent in that set B. Okay? And you can prove that this is a measure. This is called an occupation measure. Now, I want to look at the limiting object of this rho xt. So a limiting object rho is called a physical measure, which is also related to this class of measures which are called Sinai-Ruel-Bowen measures, if these occupation measures converge in a weak sense to this limiting rho for initial conditions that have a positive Lebesgue measure. Okay, so for a generic initial condition, the trajectories, they have well-defined statistical properties. So you can't know exactly where is it for the long time, but the probability of being in any patch is, can be described. Okay, so rho. And so what is the idea then is, okay, can we actually use this physical measure instead of the, can we use the physical measure as data instead of the time series? And one advantage of this is that, so sometimes you can prove that even if your sampling in time is not that frequent, you will still get, in the long time, you will still get the correct physical measure. So by design, it's actually stable under perturbations of initial conditions, because it should actually not depend on the initial conditions. Okay, so that's the key idea. So we want to, instead of matching the trajectories, we want to match these invariant measures. So the first, the way we got introduced to this was from a paper by Rob. So it's a data-driven approach to recovering dynamical systems. And what they did is the following. So they have this rho star, which is your data. So it's the samples that you see from observations of the invariant measure. And rho theta is your forward model. So it's the invariant measure produced in some way for a given set of parameters. And you want to find theta so that some distance between rho theta and rho star is minimized. And so in that paper, they looked at the Wasserstein distance, so Wasserstein 1 distance. And one of the reasons why they looked at these things is that if you have two measures that have faraway supports and you need sort of a lateral translation and then some geometric transformation to match these two things, optimal transport distances, because they're Lagrangian in their nature, they're often well suited. If you look at KL divergences or things like that, sometimes when you have disjoint supports or faraway supports, this distance is not so sensitive to these kind of transformations, whereas W1 is sensitive. I should have probably included that they have a very nice plot of the optimization landscape of F theta. So when you do this W1, it's a nice wedge, and then if you choose other distances, it has this very sharp global minimum, which is hard to catch. So that is one reason why they used this. But they had, and they were successful, but there are two challenges. And those were the challenges that our team tried to solve. Okay, first of all, to generate the forward model, they were binning long-time trajectories. So they were essentially, given a theta, they would run the dynamical system for a long time, and then they would bin the trajectories. Okay, so it's a sort of a direct approach. As a result of that, this rho theta was not differentiable in the parameter. So they didn't know how, they didn't know what would be the derivative of this forward model with respect to theta. And as a result of that, they were using derivative-free optimization for this F theta that would take a long time. So these were the two challenges. So one, it was forward model was not differentiable and was taking a long time to produce. And also you have derivative-free optimization, which might not be efficient, so you have an extra compounding computational there. So these were the two things that we tried to solve, and that's what we did. So we looked actually at the general distance, so general optimal transport distance, which is given by this, probably most of the people in the audience know this notion and the formulation. So you're given some general cost, and you're trying to find the optimal transport distance between your model and the rho star. And we looked at a general cost function, not just L1. Actually, in our case, we took it to be smooth because we needed it for some reason. So what were the changes that we made? We actually introduced a PDE-based differentiable model for rho theta, and I'll explain in a bit how we did that. So based on that model, we performed the regularity analysis of this cost or of this loss function F theta, and came up with algorithms to actually compute this gradient so that you can use derivative-based optimization, which is more efficient than the derivative-free optimization. Okay, so on the high level, these were the changes that we made on top of that paper from Rob and others. Okay, so PDE-based forward model. So the foundation of this idea is the following, that physical measures necessarily solve this partial differential equation in the weak sense. So often the invariant measure, it's going to be supported on a low dimensional manifold. So we can't hope for this thing to have classical solutions, but it has to solve this in a weak sense, and it's a straightforward computation. So if you take, if you test it against a smooth function, then basically using fundamental theorem of calculus, you can prove that this expression is equal to 0, and that's a property coming from the definition of physical measures. So we decided to use this equation, actually a regularized version of this equation, as our forward model. So given Vx theta, instead of running the trajectories for a long time, we just solve a regularized version of this PDE to produce the forward model. And the regularization that we used in this paper, which is not the only way you can do it, is this teleportation trick from Google's PageRank algorithm, which in the language of dynamical systems is something like this. You start your dynamical system, and at a random time you stop, and then you restart uniformly from the phase space. So you can think about it like that. And you can see that it's going to have a smoothing effect. Okay, so so the first thing that actually we had to solve was that, okay, we have this loss function which corresponds to the optimal transport distance between a model measure and data. So how do we compute the gradients of this, and how do we actually know that it's differentiable, right? And it was since I'm working a lot in this variational optimization related stuff, one of the most useful tricks is probably, when we're trying to differentiate stuff, is does this have, is the object that we're trying to differentiate, can it actually be represented as a value function of a certain optimization problem? So if it can be represented as a value function of a certain optimization problem, there's this beautiful formula which is called sometimes envelope formula that you can use for computing the gradients of these. And in the case of Wasserstein distances, there is an interpretation of the Wasserstein distance as an optimal value function, either in this form or through the dual form due to Kantorovich. And yesterday, Marcus was giving a talk on computing the gradients of regularized KL, and the idea there was the same. So if you want to compute the derivative of this thing with respect to theta, you represent it as a envelope function, and in this case, you take a supremum over two functions, phi and psi, that satisfy this bound, and this cost can be actually represented as this supremum. And this mu and nu should be actually rho theta and rho star. That's a typo. And we assume that our forward model is actually differentiable with respect to the parameter theta. So the question is, okay, what is the loss? What is the gradient of this loss, and when it's actually differentiable? So when we're looking at this thing, we found that it seemed that this formula was known, but we didn't find a complete analysis, differentiability analysis and etc. for this formula. And so what we did, we actually proved this rigorously and analyzed it, and I'm going to show you in a minute. But what is the basic idea? So here, if we want to differentiate this object with respect to theta, so if we would, like the naive approach, so let's say, the maximizing phi and psi, they depend on theta, right? So I can actually write that this distance is equal to phi theta plus psi theta, the integral of phi theta plus psi theta. Now, if I want to differentiate that, I should, naively, I should actually differentiate this phi and psi through theta. But the nice thing about the envelope formula and the fact that this is a value function allows you to ignore the derivative of these optimization variables with respect to parameter, and you only need to differentiate rho with respect to parameter theta. And this is how you get the derivative. So the derivative of this phi with respect to theta is simply phi x theta, which is a function that is maximizing this, times the partial derivative of rho with respect to theta. Okay, so I'm going to spend a couple of slides talking about this. So our goal was try to understand, okay, what are the rigorous conditions under which you can actually perform that operation. Otherwise, you can't use the gradient-based optimization. So there are two approaches that you can compute the gradient of this. So you see that this expression is like a composite expression. So there is a transport cost that depends on the density, and the density depends on the, or the measure depends on a parameter further. So you can use chain rule. Now you can use chain rule in two geometries. So you can use either the flat geometry or L2 geometry, or you can use the Wasserstein geometry. To do that, the answer should be the same, right? So, and you can see that, so the variational derivative of the optimal transport cost with respect to the margins are equal to the potentials from the previous page. And using that and the chain rule, you can actually come up with this formula. Or you can use the Wasserstein derivative, and after doing some derivations, you can actually arrive at the same formula. But the issue is that there are parametric models for which either this derivative doesn't exist or the Wasserstein derivative doesn't exist. So you can't just use the chain rule to justify these things. And indeed, if you're looking at, let's look at this very simple parametric model, and this can happen in real applications, right? So let's say you have a probability density which has a weight 0.5 plus some theta in the interval 0, 1 and 0.5 minus theta in this interval 2, 3, and there's a gap between these two connected components of the support. So as I keep changing theta vertically, this is a perfectly smooth, nice differentiable function. It's analytic, right? But when you compute the Wasserstein distance between two measures corresponding to theta 1 and theta 2, it's not even Lipschitz, so it's not differentiable. And the reason is that when you change theta, there's a jump happening. So if you're transporting measure, some of the measure, at least theta amount, has to a jump equal to 1 in the lateral direction, which creates this non-smooth path in the Wasserstein space. Also, because of the same reason, since you have two disconnected supports, the variational derivative of the cost function with respect to this rho is also, it's not differentiable. So this is an example where you can't, it's a clearly perfectly nice situation, but you can't compute the derivatives. And so the way to actually address this is, go through this perturbation analysis theory of value functions. And I found this wonderful book. It's by Bonans and Shapiro. I think it's called like that, Perturbation Analysis of Optimal Value Functions. And it rarely happens when you search for a theorem and its hypotheses are exactly what you need and you do not need to do extra work. So this was the case for this book. So basically, what they say is that based on this formula, you can characterize the directional derivative of this function f rigorously. Okay, you can justify all of these computations. And and the theorem that we proved based on the results from that book are as follows. So let's say you have a certain parameter theta 0. Calligraphic S theta 0 is the set of all pairs phi psi that maximize the Kantorovich potential, Kantorovich formulation. Okay, so these objects are called Kantorovich potentials. Now, if you take a direction xi, then the directional derivative of f in this direction is given by the following expression. So you take that formula that we have, but you soup over all possible optimal functions. Okay, and you can see that if you have a unique optimum, then this will lead to differentiability. But you might not have unique optimum, and so you can, since it's a supreme function, you can have like a conic type of structures, and you will have that it's actually differentiable if you pick any two optimal Kantorovich potentials, and you compute this slope, and you get the same value. So that's when you have differentiability. Okay, so if you take two different optimal functions, you compute this expression, it's giving you the same thing. So there are analogous results in the non-parametric setting for measures on finite spaces. Also, Sant'Ambrogio's applied OT for applied math mathematician's book, has analogous results for probability measures on RD, but there are no results in the parametric case, and the parametric case is a little bit more nuanced. And the main nuance is that, so if you have, let's say this is the support of your reference measure rho theta, and this is your rho star, this is a cartoon representation, and this is another situation. So in general, if you have that the supports of your reference measure are disconnected, then if you take two optimal Kantorovich potentials, their difference does not have to be the same constant over all support. If it were the same constant, we would have the differentiability, right? But if, so let's say that the measure is transported from this support to that part, and from this part to this part. If these two have a common point, if the closure of two have a common point, then even if the support is disconnected, you can prove that the difference of two optimal Kantorovich potentials is going to be constant. That will lead to differentiability of your parametric cost function, and that result is somewhat sharp. I didn't include the example here, but you can have a sharp example there. So that's the new. So basically, the typical results, they cover the case where the support is connected, but here we go beyond that and we introduce this notion of linked components, linked connected components of the support that gives you a sharper result. Okay, so another nice thing about this formula is the following. So you can prove that gradient computation is actually stable. So what do I mean by this? So let's say you know that your loss function is differentiable at some point theta 0, and you have solved the Kantorovich potential up to delta accuracy, right? So there is always a delta, so that if you solve this problem up to delta accuracy, then the gradient computation will be epsilon accurate. So if you solve the problem almost optimally, if you're sure that you solve the problem almost optimally, this computation will give you a correct gradient. So this is not a quantitative result, but it's a qualitative. And here, just a remark on the notation. So this phi superscript c is the C transform, which is a basic tool in the optimal transportation theory. Okay, so that's about that.
Quick
Yeah.
So
Mm-hmm.
in the special case of W1,
Yeah. Yeah.
is everything okay?
No, W1 is a bit tricky.
Because you have the
Yes.
so it's not,
Yes. So the thing that I was mentioning, so if you have a connected support, right? So even in this case, you can guarantee that the difference of the two potentials is constant if you have a smooth C. So, okay, at least the justification that I know works for smooth C. I don't think it's going to true be for L1, but I would not bet on that. We can discuss. But yeah, in our case, we assume that it's smooth. Yeah. And the key idea is that essentially the derivative of the cost function gives you the transport map. That is the... Okay, so that's about the sort of the differentiability analysis for the loss function. Now, what about the forward model? Well, we use good old upwinding schemes to actually solve, these problems, and we represent, this PDE as a eigenvalue problem for a column stochastic matrix. Now, unfortunately, and this you can see also on the PDE level, this might not have unique solutions, and it's in general singular PDE. But what you can do, you can introduce the following regularization. So in the I mentioned Google's PageRank regularization, you add a little bit of ones in every entry of your matrix, and you're making it a column stochastic matrix with strictly positive entries. So Perron-Frobenius theory kicks in, and this matrix is now going to have a unique leading eigenvector, which is exactly what you choose to approximate the solution of this. Okay, so you're lifting it a little bit, and then that's what you get. Now, then you can, so basically, If you approximate rho theta as a leading eigenvalue of this operator, then there are two ways to compute the gradients, right? So one, you go through the implicit function theorem, and everything should be, familiar here. The only bit that is taking, probably a little bit of computational time is this OT problem that you need to solve for both the gradient and also the value of your loss function. And here you have to solve them, because it's implicit function theorem, the number of equations you have to solve is equal to the number of parameters. You can use a more efficient way to do it through the adjoint method, where you just have to solve one linear system for the adjoint variable, and then the rest is pretty similar. Okay, so what about some efficiency gains that you can have here? Well, if you do sort of algebra and rewrite the linear equations that you get for the implicit function theorem or the adjoint method, you can actually rewrite them like this, and you get sparse matrices, and so you can use the sparsity to speed up your computations. Also, if you are using regular grids, you can take advantage of very fast methods of computing optimal transport distances and maps, and you can use this method by Matt Jacobs and Flavien Leger, if I'm pronouncing his surname correctly, which is called this back and forth method. And the nice thing about the back and forth method, so if you have a cost function that is represented, that can be that is translation invariant and separable. So, for example, just the Euclidean 2, which is pretty common, is that then you can compute these C transforms very quickly, similar to fast Fourier transform, and as a result, you can solve the OPTI problem very quickly and compute the C so anyway, you can make these computations really fast. Okay, so let me show you a couple of numerical experiments, and I'll make some concluding remarks. So in this first paper, we looked at 3 different attractors. So these are small dynamical systems, so there are not many parameters that you need to recover. So Lorentz attractor, Rossler, and Chen, and I'll just show you some things from the Lorentz attractor. So it's this well-known system of ODEs, right? So and then you have the sigma, R, and B. These are the parameters that you want to recover. And so we tested 2 cases. One is the inverse crime or manufactured solutions, where we actually take certain parameters, run forward the model, and then try to invert these true parameters. And so if we're trying to invert individual parameters, we're able to do that. So all of them can be learned. So when we're trying to learn 3 of them simultaneously, we saw that if you're doing, let's say, gradient descent in all 3 parameters simultaneously, the results are not so good. And then if you do coordinate descent, then you can recover all of the parameters. So in the non-inverse crime, we saw that, and we just tried the coordinate-wise gradient descent, and we were able to learn all of the parameters correctly. So let me talk a little bit about the further. So there are some further developments, and I think some interesting questions that we can look here. So Jonah, I think he might have graduated, but he was a student of Yunnan at Cornell, and they have a couple of actually follow-up papers, like 4 or something, and maybe Jonah's thesis is actually about that. So where they looked at different regularization techniques for the forward model, which could also take into account the noise when you're creating the data for this dynamical system. So that was one thing that they, so instead of Google's PageRank type regularization, you can actually add like viscosity regularization or other things. And they also looked at more sophisticated and large-scale parametric approximations. So we looked at just the 3 physical parameters that came with the Lorentz system. They looked at piecewise constant approximations. This is the second row. I think polynomial approximations, and also neural network approximations. And so the first line is the true data. So this is the true velocity field. This is the invariant measure. I think this is the van der Pol oscillator. This is the diffuse dynamics, and this is the non-diffused trajectory. So the first line is the true data, and then the second is a piecewise approximation of the velocity field, polynomial, and neural network. And one interesting thing that you can observe is that all of the recoveries are different. So depending on the parametrization you choose on a parametric model, although the forward model is recovered correctly, the velocity field is different. And one of the reasons is that, well, you don't have data outside of the invariant measure. So you basically don't know anything about the transient dynamics, right? And so this is a problem. So we have, one has to figure out how to solve this problem. And another issue is that if you're a stationary solution of the PDE that I wrote, it's a necessary condition, but it's not sufficient for being a physical measure. So physical measure has to kind of make you travel on the whole thing so that you're statistically, you're following the correct statistics, but this is not guaranteed. Now, one interesting question is that, are there analytic conditions on the velocity field that would guarantee that if you found the stationary solution, is that actually, is that a physical measure corresponding to that velocity field? Another interesting question would be, okay, what if you have multiple invariant measures, or it has like disconnected components, or you have these dynamical systems where the system would spend a long time in one of the attractors before transitioning into the other one, and then you've gathered data you don't know beforehand, and maybe you might be fooled to think that, okay, this is the one, the only attractor, and you miss the other one. So there are these interesting questions that that I think deserve an analysis. And yeah, I encourage you to look at these works. There's some interesting stuff going on there. And I think I will stop there. Thank you very much.